Hello, welcome to this brief podcast on the magnetic forces on charges, normally electrons, sometimes protons, as they travel through a magnetic field, as you can see from the diagram. What we've got here is an electron which is traveling around a magnetic field, and you see it tends to have a very circular route. That's because the number of different forces acting on it. And we're going to be thinking about that in more detail, and this is why this links really, really closely with circular motion. And you're going to see an example there. So first of all, think in your head. We were talking about a charged particle feels a force when it moves through a magnetic field. What factors do you think affect the size of the force? So just pin that in your head for now, and what we're going to do is we're going to work through and develop a proof for some of the rules which drive this forward, and hopefully you'll be able to identify those factors within this process. Let's start off with drift velocity. Okay? So remember, drift velocity is the average velocity a particle attains due to an electric field. And this includes the kind of random motions which are included with collisions of ions. So we've defined drift velocity in the past. It's the motion of electrons. Now, I'm going to use drift velocity to redefine current. And this is going to help us in our next step. So remember, current is the flow of charge per unit second. If I consider it in the context of drift velocity, I'm going to work like this. Current is charge divided by time. Now, if I think the amount of charge passing by, this is going to be the area of the wire multiplied by the length of the wire, multiplied by the electron density, the amount of electrons per meter cubed, multiplied by the charge of the electron, divided by time. This can be simplified a little bit because we can see within this, we've got the length divided by time, which is going to give me velocity. In fact, that gives me the drift velocity. So if we think about the length traveled divided by the period of time, this is going to be the drift velocity. So I'm bringing that drift velocity in. So the current equals nave. Now I'm going to combine this with our understanding of Bill. So this is the force which is applied or felt by a length of wire, depending on its current and depending on the strength of the magnetic field. So if I substitute the current value in for what I've just calculated, notice I've put a Q here because it's not always an electron, and this just keeps it more general. I multiply that out. So since the number of N is the electron density, or the charge density as it happens, A is the area, and L is the length, then NaL is actually the total number of charged particles. So that means that if that's the total number of charged particles, if I divide it by NaL, that gives me the number or the force on just one particle. And here we can see the force is dependent on the charge, the velocity, and the magnetic field strength. So I said that earlier on. So think about the charge, the velocity, and the magnetic field strength. These are the features which impact the force on a charged object passing through a magnetic field. So we think a bit more. When the charged particle is moving at 90 degrees to the field, the force can be calculated from force times flux density times charge times velocity. F equals BQV. And notice here, I'm going to add sine theta to the impact, because if the charged object is moving at an angle to the magnetic field, and then if I use sine theta, it means I can calculate the impact of that angle. So let's go for thinking about this. In which direction does the force act? Well, the force is always at 90 degrees to both the current and the field. Using Fleming's left-hand rule to find its direction, Now, note the left-hand rule applies for conventional current flow, so it would be the opposite direction to which the electron's traveling. Don't forget that. So a negative charging is moving to the right, has to be treated as a positive charge moving to the left. One little note there. So you must point your middle finger in the opposite direction to the movement of the negative charge. This all turns out as recognizing that the force which is applied is going to be towards the center of a circle. So if F equals ma, mass times acceleration, in this case we're going to consider the force to be equal to qvb, it's the force on the object, and mv squared over r, if you remember back, that is relating to the force required to keep an object in circular motion. So we can simplify this a little bit further. So qb equals mv over r, and therefore we can rearrange and we can find that the radius of the circle is equal, dependent on the mass of the object, the velocity of the particle, the magnetic field strength, and the charge found on the particle. This is a really useful tool which we can do for calculating when we come to cross problems. So here's my example question. A proton of mass m equals 1.67 times 10 to the minus 27 kilograms. There's a charge equivalent to an electron, 1.6 times 10 to the minus 19 coulombs, moves in a circle of radius 21 centimeters, perpendicular to a magnetic field where B equals 4,000 Gauss or 0.4 Tesla. Find the period of motion and the speed of the motion. So we're looking for how long does it take to complete one rotation. Stop for a moment, pause, try and do this calculation, then I'm going to take you through them. Okay, let's go. We know that QVB equals mv squared over r. For this, we can rearrange for v, which is the velocity of the object, and everything else is known. So that gives me a velocity of 8.05 times 10 to the 6 meters per second. I recognize that's a ludicrously high number, but we're just using this as a generic calculation. So if that's the case, then I can work out the period by recognizing that the period is going to be the distance of one circumference divided by the velocity. That gives me 1.64 times 10 to the minus 7 seconds. That's the calculation you need. So these are typical examples, and now you're going to get the chance to practice a few more in your class time.